Part A, estimate the derivative. We know derivative is slope. So at 7, 7 is in between 6 and 8. So I wrote down those 2 points right there and just did my easy slope formula. There's your rate of change there. There's your degrees Celsius on top, centimeters on the bottom. So there you go. Letter B, kind of brand new for us. The first thing we want to do when it says find the average temperature, that's your average value formula. If it gives you a problem about cupcakes and then it talks about the average number of cupcakes, that's your average value formula. So this gives us a problem about temperature, find the average temperature. That's your 1 over b times the integral from a to b. So the first thing I did on that one was jot this down. I did 1 over 8 minus 0 times the integral between 0 and 8. And here's the deal. So they're going to give us a problem like this on every single test that I've ever seen. They're going to have us approximate the integral using either a Riemann sum, which means we'll draw in some rectangles and find the area of those rectangles, or they'll say trapezoidal sum, which means we'll draw in a few trapezoids and find the area of each trapezoid. So that's why I gave us the trapezoid formula up here. The trapezoid area formula is also in your blue packets. And then so it helps me on the trapezoids to at least draw a picture for the first couple. We're going to see all scenarios. You're going to see Riemann sums, a left, right, and midpoint Riemann sum, and the trapezoidal sum multiple times. So I'm going to explain it to you each time we go through that. When we get to the Riemann sum, we get a little more practice. I think I already have a video created on some of the multiple choice that we'll do of how we can do the Riemann sum area without the use of a calculator at all. But here's all I did, as I just plotted those points, like a rough sketch of those points, like 0, 100, 193, 570. And then I just kind of drew some lines up to the curves, and then I kind of making these slanted like lines up at the top there to create the trapezoids. And then when you do the trapezoid, this first trapezoid, it's like a trapezoid on its side. So like here's the bottom of it, and then the 93 is the top of it. So those are my two parallel bases. And then the height would be this guy right here. So if I just use that formula, I'll do 100 plus the 93 divided by 2 times it by the height, which is 1. When I do the area of this trapezoid, I'll do 93 plus the 70 divided by 2 times it by the 4, and then so on and so on. So I did the same thing, just the area of that trapezoid each time. There were 4 of them, so I added up all those areas and then divide it by 8. And then thankfully, this was on the calculator part of the test, so I just plugged all that stuff into the calculator, and I should have went 0.688 right there. I don't know why I went 4 numbers. Remember, we're supposed to go 3 numbers after the decimal. Now, if they give you an average value problem, the units always agree with your original problem right there. You're just averaging out what's the average temperature of that wire. That's always going to stay those same units there. It's going to be degrees Celsius. All right, letter C I thought was pretty straightforward. When we integrate t prime, that's what they're asking us to do. When you know you're going to get the t of x, we have numbers attached, so we'll apply the fundamental theorem of calculus, and we'll plug in the top number, plug in the bottom number, and that's just t of 8 minus t of 0. They give us those numbers in our chart, 55 minus 100, to get that negative 45 degrees Celsius. And they do ask us to explain the meaning of that. And then so you're just subtracting that, the last temperature minus that first temperature there. So all that is, that just means the temperature drops 45 degrees Celsius from that heated end of the wire to the other end of that wire right there. And that negative kind of helps us out. It's going to get cooler at the other end because it's not right next to that flame right there. All right, so A through C, we'll see a bunch of stuff like that. We'll keep practicing those things there. Letter D was pretty tricky. Letter D is talking about the second derivative being positive. Is it true that the second derivative is always positive for every single x right there? Now, what first went into my mind when I saw second derivative as positive, that told me right away that the original function was concave up, but that does not help us on this particular problem right here, okay? So there's one other thing that we'll use occasionally. Let me try to connect it to something that you already know. Like if I were to tell you that the first derivative is positive, right? That means we know, that means our original function is going to be increasing. And you could apply that to any function with its derivative right there. So if I were to tell you the 100th derivative was positive, what that means is that the 99th derivative is going to be increasing, because anytime something's increasing, its derivative, its slope, is going to be positive right there. So when they told me the second derivative is positive, and that's what we're looking at here, if my second derivative is positive, that means the first derivative is going to be increasing. So if something's increasing, its slopes, its derivatives will be positive right there. So when I saw second derivative was positive, that means that the derivative is increasing. And the derivative we know is slope. So if my slopes are always increasing, then I say, yes, that assertion is true. If the slopes are not always increasing, then no, that assertion is not true. So all I did in between 0, 1, 1, 5, 5, and 6 is I found the slopes using my slope formula. So I like it subtracted 93 minus 100 over 1 minus 0, 70 minus 3, 93 over 5 minus 1, 55 minus 62 over 8 minus 6. And then so I just found a few slopes. Now, when I did the first slope, I got -7. The second slope, I got -5. So from this slope to this slope, that slope did check off. That slope was increasing. It did go higher, negative number, so it went increased right there. But then your next interval, the slope went from -5 to -8, and it decreased. Okay, so if it decreased, that means that T prime was decreasing, the slope was decreasing right there. And then so I just mentioned, so since that T prime decreased, that second derivative is not always positive right there. So I thought that was a little tricky, but you know, we're learning as we're going through these things and just applying some of these properties right here. Salsa.